Hi viewers, now I am going to discuss on the topic F by D ratio spillover and F by D calculation. So here, this is like continuation for parabolic reflector antenna concept. Here, what is first F by D ratio? We'll see. So F is nothing but focal length and D is nothing but the diameter, or otherwise we can call it as aperture width also. So we will see one by one. F by D ratio is nothing but, for example, if you take a feed system, to properly manage the feed system or to properly make the feed system to operate, the most important thing is the calculation of F by D ratio. So to ensure that the antenna operates correctly, it is necessary to ensure that the radiating element is placed at the focal point. So to determine this, it is necessary to know the focal length. So we know already what is focal length. Focal length is nothing but the, see here, if you take the antenna element like this, here if you place your feed element here, the distance from vertex point to focal point, this is called as a focal length. So, and the width, this one is called as diameter or aperture width. The ratio of these two things is nothing but the F by D ratio. So to determine this focal length, we need to have some calculation part. How to get that focal length or focal distance, that we will discuss in this topic. So in case of parabolites, the ratio of focal length to dish diameter is simply F by D ratio. So the most important point we have to keep in mind is, if the F by D ratio is often specified along with diameter, it can be obtained very easily by multiplying F by D ratio by the specified diameter D. That means very simple. See, if you are designing a parabolic dish like this, so we can know the D value, right? So based on this D value, we are going to calculate the value of F. So that is the thing we are going to do in the upcoming slides. See here, we'll just have a small conversation here. What happens if the F by D value is larger, F by D value is lower? What happens? We'll see. As we are going to take a higher F by D ratio, what happens is, if this is our parabolic reflector, if our F by D ratio is very long, means say, for example, we are placing our focus point here, what happens? The illumination range over this reflector surface will be shallow. That means it is not very deep. So that case, we will consider it as a shallow counter. When F by D ratio is very low, that means it indicates our focal point is very nearer, say, for example, like this here. So in that case, the illumination will be very nearer to the surface of the reflector. In such case, it represents a deep hole. That means illumination is in depth. So the minimum, what is the correct value of F by D that to be maintained? So after the standard experiments and after the standard mathematical analysis, the value determined is 0.25 or 1 by 4, which places the focal point directly on the plane of aperture area. So that means if you, this is your parabolic reflector, exactly at this point, we will be getting the value of 0.25 as a standard value. In antenna design, a small value of F by D ratio requires a feed horn that has wider beam. See here, the effect of F by D ratio value will fall on the feed antenna also. So horns, based on the horn design also, will be getting wider beam widths, narrower beam width. So according to F by D ratio, the selection of horn also should be made properly. So as a smaller F by D ratio, the horn should have wider beam, and F by D ratio is larger, means we will go for narrow beam width in a horn antenna. Here for F by D ratio calculation, why it's so important is because of this spillover effect. So what is spillover? Spilling means like splitting or like distribution. In that simple way we can understand. Say for example, this is our reflector surface. I have placed a source here, that is nothing but some feed point or active element, whatever we call it as active antenna. If we place like this, if you start giving a external supply to this element, automatically it starts producing radiation in all the directions like this. If you observe clearly, only this part of the reflector surface is illuminated and which is required. What about all this rest of the thing? This part we call it as a spillover, and which is unwanted or not desired for our output radiation pattern. And along with this, one more drawback is also coming here. For example, these radiations, they are moving out into outer space, which does not cause much drawback. But if you observe here at this end, that means to this point. So at this point, if you observe, see what is happening, all the rays that are reflected from reflector are coming towards in this direction. But if you observe properly, directly, this we call it as primary antenna, this as secondary. Directly the rays from the primary antenna are getting obstruction for the, are giving obstruction for the parallel rays that are coming from reflector. So here what happens, these two gets interfering. So that type of all the rays, we call it as a back lobes, which are not at all necessary for a parabolic reflector output. So if you did not take a proper F by D value, these are the drawbacks that are occurring in the parabolic reflector antenna. How to overcome these drawbacks is properly choosing the F by D value. See, F by D ratio, how to choose this one? We are going to take example of 3 cases when F by D less than 0.25, equal as well as greater. See the first diagram, this is a parabolic reflector surface and this is my focal point F. So in the first case, what I have done, focus inside the aperture plane. This we call it as aperture plane. So, and our focus is internally placed with respect to the aperture plane. So here what happened, after exciting this focal point, the rays are coming outward like this. If you see the distance from this reflector surface to the focal point, it is very small. That means the focal length F is very, very smaller than the first case. Coming to the second case, the focal length or focal distance is little bit larger compared to the first case. You can take a reference here. So, and this is the D. D is common in all the cases. I have marked here. You can take reference from there. So, in the second case, F by D is exactly 0.25. That means I have placed my focal point exactly at the aperture opening. Third case, what happened? I have moved out of my aperture. So, this is the aperture opening, but I have placed my focal point far away from the aperture. So, here in this case, the focal distance is from here, we'll take as reference here to here. So this is the focal distance. See, compared to first two cases here, the focal length has been increased a lot. So in this case, what is happening? This is the aperture endpoints. Out of this aperture area, the radiation is coming out, which is called as spillover effect, not at all required. In the first case, this part of area is not at all excited. This part of area is not at all illuminated. So what does it indicate? The first case, the surface of reflector can't be properly illuminated. In the final case, the unwanted spillover effect is occurring. So in order to get proper F by D ratio, this is the correct way of taking the value of F by D ratio. How can we decide? It is exactly 0.25. Just orally, we cannot say that. So mathematically, we are going to see a small analysis. So when feeding a parabolic reflector antenna, it is necessary to place the radiating element at focal point. This already I have mentioned. So if focal point is placed properly, all the reflector rays will be concentrated according to our requirement, that is in the forward direction. If feed antenna is placed at proper focal point, so the main advantage we get is maximum gain is achieved and the proper operation is maintained. So how to know the focal length? That is our main point here. It is calculated with the help of following equation. So now this is our mathematical analysis for the F by D ratio calculation. So F by D is nothing but F is equal D by 4 cot theta by 2. 1 by 4 just we take it as 0.25. F is equal D 0.25 into cot theta by 2. That is nothing but F by D is equal 0.25 cot theta by 2. How we are saying this as a standard value? We'll look into this diagram. See here, I have taken a reflector surface. So this is in this diagram, this reflector is a plane one. If you start rotation about the axis O dash, it will take the surface as a paraboloid. That is nothing but three-dimensional part. So here, this is our focal point, and this is the aperture width or diameter opening or anyway that I have mentioned here. The same D, you just imagine at this dotted line part. And this is the distance R. Even as PQ is defined, which will be equal to Z0 distance. And this part, this total D means this is D by 2 as well as this is D by 2. And O dash is the axis of parabola. So majorly here, we are going to consider a surface geometry such that the plane which is passing through focus is perpendicular to the axis of reflector, right? So we know the definition of parabola. What is that? The locus of a point is equidistant throughout this, whatever the area we take over the reflector, everywhere the length of the lines are equal. So for example, FP plus PQ is equal to a constant value. Say for example, if I take another value, somewhere Q here, somewhere R here, and R dash here, or whatever may be, that also becomes equal. So that we call it as definition of parabola. So FP plus PQ is equal twice of F. It is nothing but twice of your focal distance. So that I am going to refer as like this. FP is equal to R, as already I have mentioned the radial distance R, and PQ is equal to R cos phi. If you consider this part as right angle triangle, what is cos? Nothing but adjacent by hypotenuse. So PQ is nothing but this adjacent side hypotenuse that I have rewritten as PQ is equal to R cos phi. So from the above equation, what we can say, FP plus PQ is equal to 2F. That is nothing but R plus R cos phi is equal to 2F. So take R as a common, we get R into 1 plus cos phi is equal to 2F. So bring this R this side, we'll be getting 2F by 1 plus cos phi. From this, I can write this 1 plus cos phi. See, this 2 is brought down. So 1 plus cos phi by 2 means just rewrite it as cos square phi by 2. So 1 by cos square is nothing but secant square. So here the value of R we got is F secant square phi by 2. And now what is the thing we are going to do is the same paraboloid, if we make a revolution about O dash, we will be getting the coordinates x0, y0, z0. But it does not change the value of phi. So the symmetry will be remained as usual. In order to move over the analysis, we are going to rewrite in the terms of rectangular coordinates x, y, and z. So here, what is FP plus PQ is, it's nothing but R plus R cos phi. So that we have rewritten as R plus R cos phi is equal square root of x square plus y square plus z square, and R cos phi is nothing but equal to z. So that you can refer in the above also. Just we are writing in terms of rectangular coordinates. That's it, okay? Which is again equal to 2F. Why? Because R plus R cos phi is nothing but FP plus PQ. Now, if you just take over the mathematical part, just send the z that side, as well as remove the square root, squaring on both sides. We'll get cancellation of z square. So what is left over? X square plus y square is equal to 4F into F minus z. So here a key point you need to notice, x square plus y square, we are going to take the condition less than or equal to d by 2 square. So here what is the d by 2? Half of the aperture width, right? The squaring of these two can't be greater than this one. So from Pythagoras rule, we can know that, right? Sorry, from hypotenuse rule, we are going to take the condition x square plus y square less than or equal to d by 2 whole square. So with the same thing, we are just going to continuation in the next one. See here, the expression we have got is F. So here, we are going to calculate the expression of F by D with the help of angle theta. So here, tan theta is equal d by 2 by z0. So how we got this one is just we will go with reference of previous one. See here, this is right angle triangle. from this right angle triangle, we got our tan theta value. Tan is nothing but opposite by adjacent side. So taking that as reference, we have obtained the expression tan theta is equal d by 2 by z naught. So z naught is nothing but distance between focal point to edge of the reflector. That from the diagram itself we can understand. So now previous equation x naught square plus y naught square is called 4f into f minus z naught. So in that f minus z naught is just separated and the 4f is sent to that side. So from here we will get the value of z naught is equal to f minus x naught square plus y naught square by 4f. So just by having z naught is equal to f minus, replacing this x naught square plus y naught square is equal to z by, less than or equal to d by 2. I'm going to take the case of equality. So it is replaced as d by 2 whole square by 4f. Now, just squaring this, we'll get f minus d square by 16f. So from that, tan theta is equal to d by 2 by z naught value we have replaced. In this equation, we have replaced the z naught value. And here, for tan theta, we are having number of formulas. Out of that, we have replaced here this tan with 2 tan theta by 2 by 1 minus tan square theta by 2. So that equal to d by 2 by f minus d square by 16f. Just made it as equal. Tan we have written in another form. Just here we got 2 tan theta by 2 into cross multiplication of both of these. We will get this equation. From here, you just send all the terms to that side, this denominator term. We got the cancellation of these. From here, 2 into 16f square minus d square into tan theta by 2 is equal to 8fd minus 8fd tan square theta by 2. Right? So from this, just made the terms all one side and make it as equal to 0. So this equation we can take into form of minus b plus or minus square root of b square minus 4ac by 2a. I have written the entire equation in that form, a, b, c. So after taking this entire form, just simplify that, we will get tan theta by 2 is equal 16f square minus d square equal square root of 16f square minus d square whole square plus 64f square d square by minus 8ft. So write this equation again, we are reframing in the form of this one. See here, a minus b whole square plus 4ab is nothing but equal to a plus b whole square. We have reframed the equation in that way. We got 16f square minus d square plus or minus 16f square plus d square. That is nothing but a plus b whole square form I have taken, denominator as usual. From these two terms got cancelled. And what is left over here finally? Tan theta by 2 is equal to d by 4f. So nothing but tan theta by 2 is equal to d by 4f. Out of this, just rearrange the terms. We get f is equal to d by 4 cot theta by 2. Nothing but tan is got this side. It is replaced with cot theta by 2. So 1 by 4, what is the value? Already we know it is nothing but 0.25. So from this finally what we achieved, what we have said in the previous slide, f by d is equal to 1 by 4 cot theta by 2. The same thing we have achieved finally. So taking this as reference, in this diagram, we have said that f by d is equal to 0.25 is the reference value. That is, if we place the focal point exactly at the mouth of the reflector, then we can achieve the proper focal length or focal distance. Thank you.